It is a great pleasure for me to welcome you all to the webinar on solving and visualizing physics problems using Mathematica. In association with Academy of Physics, Teachers Kerala, Wolfram Research USA, and GT Enterprises Bangalore, organized as part of skill development program of the Department of Physics during this year. As you know, teaching physics, it is sometimes feel very difficult to visualize many of the problems, as well as sometimes it is a lot of equations could be there. The complexity of the equations will harness the understanding when the equations becomes more and more, as well as the situations when complex equations are coming. One of the problems I can cite is the tunneling problem, which we always qualitatively discuss, but unfortunately we just frame the equations and forget about the later part. So in that way, Mathematica gives an opportunity to visualize as well as manipulate with different parameters of the problem. That is the importance of Mathematica. When I was doing my PhD, as you know that this book has been table of integrals, has been a handbook. Whenever we go home, we take it because we have to solve it. But right now, I kept it in my shelf for almost 15 years. I'm not using because I am using Mathematica. In addition to that, when you deal with experimental physics, we have to do a lot of solutions on mathematical equations. So at that time, sometimes we do the solutions, but unfortunately we will get each time different solution because of our limitation. So the power of Mathematica comes. It does all the symbolic mathematical calculations as well as the provision for visualizing and manipulating simultaneously. That is the power which makes it superior than other softwares. So with this introduction, I am coming to my duty to welcome all the dignitaries as well as all the participants gathered here in this webinar. So first and foremost, I welcome our Honorable Vice Chancellor. He is an eminent professor in physics, and we are very lucky to have him here, being a very good professor and teacher and a champion of material science and a good administrator, and finally, after all, he is a very good human being. So it is great pleasure we welcome you to this program. Welcome you, sir.
Thank you.
Second, we have the Professor G. Govindaraj. He's the former dean and professor of physics, and I attended a lot of classes of his, and wonderfully speaking, he's a champion of Mathematica and a very good teacher with in-depth knowledge in almost all fields of physics. So it is a great pleasure. I can't see no one other than you in India for teaching Mathematica. With these words, I welcome you, sir.
Yeah.
Next, we have all the programs of physics department has been chaired by or motivated by our head of the department. He has been behind all the activities where our department could make its presence in the forefront of the University of Calicut. Sir, I welcome you to this program, Vinod sir. Next, we have a very good collaborator for this program, the Secretary of Academy of Physics Teachers, G. Harikrishnan. He is the Associate Professor of Physics in Government College of Madapalli, and he's a very good organizer, and he is keen in popularizing physics throughout Kerala by inviting many eminent professors, very good teachers all over India, and giving us an opportunity to listen. Dr. G. Harikrishnan, I welcome you to this program.
Thank you.
Now we have Dr. Anthony Joseph. He is the director of School of Physical Sciences in University of Calicut. He's a very good motivator. He's the leader of physics, faculty of physics, and he's a very good teacher and good motivator. Sir, I welcome you to this program.
Thank you.
Now, I welcome all the colleagues of mine in the Department of Physics, then a lot of professors from different universities, different institutions, colleges are here, many research scholars, good number of students, all are here. I welcome each one of you personally as well as on behalf of this program. And I should mention Mathematica as collaboration, Wolfram Research collaboration, and GT Enterprises, the Indian distributor of Mathematica. So I have to tell you, they have provided 1 month license along with 1 month free training. Training in the sense, if you have any problems, we can online contact them. So based on our program, we have made a WhatsApp group, we have made a email group. Anyone has any problem, you can contact the group, others will solve you. In case any technical need, support is needed, we will also get support from Wolfram Research. So with these words, I welcome you all once again. I request our head of the department to chair the session.
Honorable Vice Chancellor, Professor M.K. Jairaj, sir, Professor G. Govindaraj from Pondicherry University, Dr. Hari Krishnan, Secretary of Academy of Physics Teachers, Kerala, and Professor Anthony Joseph, School Director, Physical Sciences, and coordinator of this program, Mohammad Shahin Tayil, and other faculty members from different institutes, universities, and colleges, and faculty from our own department, and my dear students. So, of course, we are going through this epidemic problem for a long time now. Our department were organizing many this type of programs, skill development type of programs in the past. So we have been conducting such programs. Mohammad Shahin Tayil was many of the programs he has coordinated earlier. So, of course, this is probably this may not be the ideal way of doing this Mathematica type of programs in the skill development. It needs probably hands-on training, but we are trying our best to impart some knowledge, at least for some students, and maybe a percentage of the students and attendees may benefit from this type of skill development. And I used to wonder, the Byju's programs, maybe the success of Byju's programs may be because of the graphical adoption of these programs, not Mathematica. I don't know what they use, but still, if you see these programs, you will see that their success maybe is showing the physics or other sciences in the graphical formats, and that gives them advantage in the market. So there are skill development is really I believe it should be a part of any of the postgraduate programs, so that not only in Mathematica, in some other fields, maybe in the other sides, so maybe in the English, maybe literature, some other way, but it should be part of the maybe the course itself in the PG programs. So I do not want to prolong this saying more things, but I would say that this type of programs surely benefit a large number of participants, and they will take away the good things from Professor Govindaraj, and he is leading this program. So, on behalf of the department, again, I welcome everybody to this program and invite Professor M.K. Jairaj, our Honorable Vice Chancellor, to inaugurate this program.
Good afternoon. Am I audible?
Yes, sir. Yes.
Yes, sir.
Good afternoon. Professor Vinod Kumar, Head of the Department. Professor Govindaraj, today's keynote speaker, former Professor of Physics and Dean of School of Physical and Chemical Sciences, Pondicherry University. Professor Anthony Joseph, Director of the School of Physical Science. Dr. Shaheen Tail, Department of Physics. Dr. Hari Krishnan, Secretary, Academy of Physics Teachers. Dear participants, students, and friends. First of all, I congratulate Department of Physics for initiating such an activity, along with the Academy of Physics Teachers in collaboration with Wolfram Research and GET Enterprises. I can see that there is about 170 participants in this workshop. Maybe the involvement of Academy of Physics Teachers given a wide publicity, and nobody has to say the importance of the Mathematica for a physics community. I can again congratulate the initiative by Physics Department and APT for introducing the students the tool of Mathematica. As all of you know, any scientific discovery or understanding involves the formulation of theory to explain the observed phenomena. We design and execute experiments to test the theory and the feedback of experimental results to evolve the theory. So this is basically a loop, and keep on improving ourselves in the understanding of the phenomena. This process is known as the scientific method and play a key role in any scientific discovery. So the question is, where lies the modeling and simulation in the loop of experiment and theory? Modeling and simulation is in fact lies at an intersection between the theory and an experiment. One hand, we can model and its associated implementation in software like simulation tools are an expression of theory itself. On the other hand, the execution of that software that running the simulation and collection of results from it can be viewed as a virtual experiment. A fundamental question becomes, to what extent can the results from a simulated or virtual experiment be trusted? This question often arises even for actual experiments in the real world too, but it's doubly important that substantially more challenging to answer for a simulated and virtual experiments. It's involved validation, verification, and the uncertainty quantification of the simulation software as well as the data it consumes and produces. Instead of modeling and simulation are highly valued in scientific discovery because they provide additional insights and that are often impartial or impossible to discover through real world. Experimental and theoretical analysis alone. Modeling and simulation serve to complement and inform the experimental and the theoretical arms of the scientific method. While the traditional simulation systems tend to focus on a particular area, Mathematica not only provides broad multi-paradigm modeling and computation, but also includes a unique support for complete simulation project workflow. I need not to stress the importance of Mathematica to a physics community. I know that you are all eagerly waiting for the inputs from and training from Professor Govindaraj. I hope that this is the beginning and the students can gain more knowledge about the Mathematica through interaction between the experts. In the pandemic time, it is difficult to have a hands-on experience, but you can have webinars and interaction through online, and you can enrich yourself in the area of Mathematica, which will be useful for your future, not only for master's students, it's also important for research scholars who are working both in experimental and theoretical physics. Especially experimentalists need to have some kind of theoretical support and modeling. So I believe that Mathematica will help all of you in achieving your goals. And with these words, I declare this webinar open. Thank you all.
Thank you, sir.
Thank you, sir. So next is Professor G. Govindaraj will deliver the keynote address. Welcome, sir.
DG sir, please unmute the.
Sir, you have to unmute.
Yeah, good afternoon to all of you. So, respected Vice Chancellor, Professor M. Jayaraj, University of Calicut, Director, School of Physical Science, University of Calicut, Professor Anthony Joseph, and Professor A.M. Vinod Kumar, Head Department of Physics, Dr. H. Harikrishnan, Associate Professor in the college, Government College. He is an APT of in Kerala, and Dr. M. Shahin. So it's a great pleasure for me to be participated in this seminar program, which is on the solving and visualizing the physics problem using Mathematica. So I have been associated with this Mathematica from the year 1998 onwards. So it's close to 24, 25 years, 20 years, more than 20 years. In fact, I started my career starting with the numerical techniques using photons. And then slowly, at that time, this has been introduced by Stephen Wolfram in the year 1988. So I started looking at his text, even the volume 1, first release of the Mathematica version 1. I have a copy of the textbook also now. Then it was in a DOS version, it was too difficult to use, but still at that time it is a great achievement to do symbolic algebra with the desktop computers. Then slowly over the years, this has really emerged as a big tool for the entire science, engineering, and technology. And you can do great many things, as our Vice Chancellor was telling, that it is possible to connect experiment and modeling through the simulation and animations, and you can visualize things, what is going to happen experimentally, what is happening theoretically, and this connection is really goes together or not, all that can be exhausted. In fact, in this presentation, I planned certain basic things, starting from dropping a stone from a particular height. What is the dynamics that goes in? Can we understand all about it, starting from there? Then go to the next problem of radiation problem, black body radiation. How do we understand then what is the information that you can get it? How much one can understand through the Mathematica? Like this, you have a wave packet evolution. Then you have the wave packet evolution through the barriers and wells, then hydrogen atom problems. See, all these things we know we have been learning that, but you can see the depth, how much you are able to get it by using such tools. And not only that, it is so accessible for you to vary the parameters. One can provide with the variable parameter to the students or to the learners. They're so comfortable with that they can figure out what is really happening. Okay, when you change the parameters in every one of the problem, what we try to look at. For example, dropping two different weights at a particular height, it reaches the ground at the same time. But what is the mechanism which goes in? What is happening dynamically? Can I really look at all this dynamic that is happening around? Similarly, when you look at the black body radiation for a given temperature, you have a spectrum. I change the temperature or raise it. There is a change in the spectrum. Okay, there is a smaller value at low frequency, higher value at the close to zero spectrum. In between, something happens. Now, what is that really happens, or what physics is responsible for the nature of the curve what you are obtaining? If you want to have that kind of an understanding, when you start use this kind of software which is available to animate and generate the symbolically and numerically, you would really feel that there is a lot of learning that goes into it. Now, the problem what has taken for 20 years that can be learned by 2-3 years time by the present generation. And there are symbolic algebras. For example, you can do the typical thing like Fourier transform, Laplace transform, convolution. Okay, one can visualize this mathematics. I can visualize what is the Fourier transform. Visually, I can feel. Visually, I can see convolution. Visually, I can see what is the power spectrum. Okay, mathematics can be converted in the form of pictures, and we can feel it, and that we will adapt to an experimental situation and try to connect experiment to this theory and then see how things can be done. And is there any possible way that something being approximated or assumed, can I improve that assumption? You improve that assumption, look at things what happen. So all these possibilities that are there with kind of Mathematica. In fact, after my superannuation, I have given 2 courses now. One of them fully on Mathematica, about the Mathematica, about 48 hours of lectures, 30 to 1.5 hour sessions. And there are many people that attended online and provided whatever possible. Exactly same thing I done for another course, which is my research area on the dielectric spectroscopy. How do we handle dielectric spectroscopy results or analysis by using the Mathematica? And then what do we understand in terms of the dynamics of the charge carriers and in terms of the dynamics of the dipoles? So all this could be able to do it. And there is a research component, it goes enormously when you try to learn such things. So I'm going to make all this demonstrations, some of the typical demonstrations, whatever possible within the time that's not available. And we will see most of the details when you start my presentation. With these few words, probably when I make my presentation, you'll come to know more about the Mathematica and its potential use. Okay, with these few words, I thank the organizers for giving me this opportunity, and we start the session after 5. Thank you.
Thank you, sir.
Thank you, sir.
So next is felicitation by Professor Anthony Joseph.
Respected Vice Chancellor of the University of Calicut, Professor M.K. Jairaj sir, Dr. M. Vinod Kumar, Head of the Department of Physics, University of Calicut, Dr. G. Govindaraj, former Professor and Dean of School of Physical and Chemical Sciences, Pondicherry University, Dr. M. Shahin, the coordinator of this program, Dr. G. Harikrishnan, Secretary of APT and Associate Professor from Government College Madapalli, my colleagues, teachers from colleges and other participants. Since most of the participants are students, especially postgraduate students, let me mention a few points before going into my duty. As we all know, physics as a subject addresses fundamental questions regarding space, time, energy, matter, motion, and interactions. From the time of Isaac Newton, physics was known as natural philosophy.
Yeah, Ganesh.
Ultimately, mechanics. The foundations of physics are built upon the four ramifications of mechanics, namely classical mechanics, quantum mechanics, electrodynamics, and statistical mechanics. These four subjects are the foundation subjects in physics. Any branch of physics which has its roots in the soil
Yeah,
of mechanics
dear.
grows as a powerful branch of physics. Otherwise, it develops as non-physics. The subjects other than the foundation subjects are called the frontier subjects. Frontier subjects are those in which current researches are going on, such as atomic physics, molecular physics, nuclear physics, solid state physics, material science, astrophysics, etc. Mathematics, mathematical physics is a theoretical tool. Mathematics is for theoretical study and electronics is for experimental study. Both are tools. From the writer, we can see that Dr. Govindaraj has selected the four foundation subjects to demonstrate how to solve and visualize physics problems. Two important aspects related to physics are learning it through analysis and visualizing the results through an appropriate technique. So, as we have seen, Dr. Stephen Wolfram, the founder of Mathematica software, is by training a theoretical physicist in high energy physics and quantum field theory and also in cosmology. So he is considered as one of the pioneers in the field of scientific computing. It is a happy thing that we are going to be trained in the use of Mathematica by the most apt person in this field, Professor Govindaraj. Thank you, sir, for accepting our invitation and becoming the mentor to this short course.
Thank you. Thank you, Anthony, sir. So next is for felicitation, I invite Dr. G. Harikrishnan, Secretary of APT.
Good afternoon, Honorable Vice Chancellor Professor Jairaj sir, our resource person Govindaraj sir, and Department Head Vinod Kumar sir, Anthony Joseph sir, Coordinator Shahin sir, and dear participants. The number of the participants, I think it's reached 212 now. Many teachers, many of them APT members are present, and a lot of students are also present. And I request all the participants to make the most use of this opportunity. You have heard that our coordinator has stated that the Indian distributor of this Mathematica has given free license to all the participants for 1 month. So you can practice Mathematica during this period. And I think I request Govindaraj sir to mention about this Mathematica cloud facility also, which is freely available so that students can continue the practice of Mathematica. And I think Shahin sir earlier told me that student versions of Mathematica or student license is available for a nominal fee. So those who can afford it, researchers, etc., those who can afford it can think about taking that license. And also, these two WhatsApp groups are present for helping the participants so that they can continue clearing their doubts. And so I wish all the success to this program, to this commendable effort from Department of Physics, University of Calicut, and Coordinator Shahin. And I thank this opportunity. Thank the coordinator for giving this opportunity. Thank you all.
Thank you, Hari Krishnan. So we will go to the program, and I invite Dr. Govindaraj again for the session.
Yeah. You can start the session now.
Shahin?
Yes, sir. You can start, sir.
Yeah. So am I audible for all of you?
Yes, sir. Audible.
Yes, sir.
Screen also clear for all of you.
Screen not yet come. I'll see that. So you can.
Just check. Screen has come or yet to come?
No, it is still loading.
Oh, I see.
It's saying it is viewing Dr. Govindaraj's screen, but nothing has come on the screen. The page is empty, or
No.
no? Okay, it is that viewers' symbols are on the screen, but no content.
1 minute. I'll just check one more time.
Hello, sir. You have the freedom to for presenting according to the system administrator. So can you close it once again, your presentation, and try to open it?
Well, I have to close for a while. Again?
Say close the presentation and open it. Like.
Okay. 1 minute. I'll just go to that.
Yeah.
Stop sharing. Okay. Now I'll start now.
Yes, sir.
Start. Is it coming now?
Yeah, now came. Now you can make
okay?
it. Yeah, now it is okay.
It's clear now for all the slides.
Yes, sir. Now it is clear.
Okay, that's right. So I can start now. So good afternoon to all of you. So if there is any issue, you can just call me in between. Suppose if this gets stuck now, audio
Sure,
or
sir.
video. Yeah, you just give me my mobile with me. Okay, just send a call to me so that I can cross check it and we'll correct it. Okay.
Okay, sir. I will do that.
Right. So this is what my title of the presentation: Mathematica method, interactive method in solving and visualizing physics problems using Mathematica. So this is the plan of my presentation. This is the outline. So a few words about our university and then my contribution to the teaching and research and growth of the university. There are some inspiring quotes by the people, scientists. Then introduction to solving and visualizing physics, mathematics, chemistry, science and biology. And physics, what will you do and how will you do growth of physics? Solving and visualizing the Mathematica problem, where Mathematica is a set of powerful skills for turning ideas into reality. So there are powerful tools that are available to turn your ideas into reality. And then solving and visualizing the physics problem. First is dynamics of free fall and accelerating objects, the radiation problem, birth of quantum physics, wave motion, quantum wells and barriers, energy bands in solids, and then electrodynamics, you have a gradient, del and curl, what are they? I do not know whether I can complete all of them, but whatever is possible, we try to see that we have some ideas that is going to emerge by using this kind of a powerful software. So this is what our university location. It is there in the Pondicherry somewhere here, and it is about 140 kilometers from Chennai. And these are the present position or present strength of the departments, and then various departments, and these are the affiliated institution. And I have completed 30 years work in teaching as a teaching faculty, various levels, and including vice chancellors in charge for the Pondicherry University for some time. So this is what my background in the Pondicherry University, and this is what your entrance. Okay, and what is the contribution towards my research? These are the journals, research journal over the period of time I have published, and these are the number of publications, and this is the various works in the workers in the national and international level, and their contacts and their interaction. They are all interacted. Continues to have an interaction with these people. Some of them are past old people. Some are alive. They are very active now. These are some of the people in which I have the contacts, and then there is an interaction. There is something being contributed also, and all being compiled now in the form of a. We have some interesting research that I'm putting in the form of a textbook, Dialectic for Impedance Spectroscopy with Mathematica, Understanding Dipole and Charge Carrier Motion. This is under preparation, and I hope another year time or so I would like to complete that. And what about the contribution to the university? This is my contribution to the university in terms of establishing the facilities. Like you can see the 25 major facilities that are being established during my tenure as a coordinator of the center, and this experience gained a lot for me to learn many things about the experiments, and then physical ideas, principle with which instruments are being operated. So this really helped me learn a lot to learn, and these are the facilities that are available, and there are many users now, and our publication level has raised in the university. Impact factors, everything has been raised because of these facilities that have been established in our university. Starting from 2005 up to 2018-19, I was there. 19 till 19, I was there, and as a dean also, I have been able to develop many things in the center. So this is what my contribution in terms of research, and of course, in the teaching parts, I started developing interactive part of the material in the year. This is 1999. The year 1999, I was away for 1 year at this place. At that time, there is not much facility, research facility at this place. Then started publishing this work, whatever has been developed for the teaching purpose, this interactive computation and the simulation of black body radiation. I started using at that time itself the Mathematica. So this is published in the year 1996 Education in India. So now this is being compiled, and along with the other papers, this is the simulation of quantum wave packets, evolution and propagation through the potential and interactive approach. And you can see this is another interesting aspect. So the interactive package has been developed, and the parameters have been varied, and that's all given in the form of manipulative materials. You can really see the variation of the parameters, like wave packet width can be changed, energy can be, or velocity can be changed, and see when the propagation, with respect to propagation, how things are happening. Now it is still much easier to do. At that time, I have tried, but I did it with Fortran and little bit on Mathematica. Now it is amazing with the kind of techniques that have been developed in Mathematica. You can really see things elegant way, and you can do the wonderful algebra also. And this is the inspiring quote which I experienced personally myself. I have greatly experienced the words of our great scientist and most respected past president of our country, Dr. A.P.J. Abdul Kalam. So learning is creativity. Creativity leads thinking. Thinking provides knowledge. Knowledge makes you great. So this is very much I experienced over the years, and thinking is a capital. Enterprise is the way, and this is most important. Hard work is the solution, which I have experienced over several years, starting from my PhD career onwards. I feel that there is something has been done and something has been contributed. And according to the Feynman view on science, if any scientific idea proposed disagrees with experiment, whatever be the nature of the experiment, okay, if it disagrees means it is wrong. There's no question about it. So you have to have whatever the idea which you give, either in terms of experiment or a model, that all both experiment theories should go together. And another thing is, once he said in the class, you do not know anything until you have practiced. Unless you practice, you cannot learn things. And if you follow certain steps, okay, like procedures, steps of this procedure. Conceptualize things, categorize, analyze, and finalize. Okay, if you do that, you will find easier to come up with a solution, gain more from your efforts. And another interesting aspect from these great people, we cannot solve the problems with the same thinking when we created them. So we need to have a different kind of thinking now when you look at the problems. And if you wanted to impress people, make things complicated. If you want to help people, make things simple. So in fact, this is what I would like to do. I want to make people to help people, so make things simple. So that's what we try to do through this Mathematica with all this mathematics and the visualization effect. We try to do this. So now you can see visualization of the topics. Now you can see, we say there's a physics, and you can see how this physics has been branched out. So this is the kind of visualization which means once I say, this all automatically comes to our mind. Then what we will do, so this is actually the hyperphysics which is available, and this is actually created by this CR Neil, Georgia State University. It's one of the fantastic software tool that is available for learning physics. And if I click mechanics, and you can see visualize it again, mechanics, you see what are the things that are there, and which will be most of the time you'll be learning. And keep track of things and connect them properly and go from one to the other. That practice once if you learn, then it will be possible for you, your learning process will be much easier, and you will be able to connect it and you will be able to remember things, what are the formula or expressions you need to have, and what would be the physical idea that is involved. All this that can be done. With all this understanding, only people have created such links. Okay, so for example, you take this mechanics, you have velocity and acceleration, you have a periodic motion, and then you have Newton's law, mass, force, and gravity, work energy starts from here, it comes through this connected here also, conservation of momentum, conservation of angular momentum, energy, then circular motion. You see the things have been very nicely connected. For example, this is mechanics, and if you go to the electrodynamics, you can see electricity and magnetism. I don't have to tell the application of this. Okay, life becomes impossible now if you don't have this chemistry and magnetism. Okay, now you can see the things that are get connected to each other, and this goes and sits over here, okay, along with the main part of our physics lane. So like this, every topic that is being generated like this, and really that visually that has been created, and one can really note down all these things and keep track of them and try to understand things. Okay, that will be very easy, and you can remember things, many things that you can remember, okay, through such things, including mathematics. Visualize the mathematics through this. You have trigonometry, algebra. This all will be used in our physics courses. You cannot escape from any one of these mathematics. If you escape, then you are not going to do a good physics. It's not possible to generate a proper or a good physics where you have the combination of your experiment and modeling that will fail. So in fact, physics, mathematics is the language of physics. So it is impossible for us. We should have a in-depth knowledge about these things. For example, what do you mean by an exponent? I spend so much of time to understand about what is the E. Through Mathematica, there are many things that have been done to understand about E. So there are one of them. Similarly, differentiation. What do you mean by a differentiation? What do you mean by differential equation? Vectors, eigenvalue, eigenfunctions, okay, geometries. So algebras and connection to the geometry and vectors, the linear algebra, all are integral part of our courses. So therefore, it's necessary to have some connections between them and between to the maths. You're not going to focus on mathematics part of it, but our focus may be on physics, but you need to have the knowledge about this mathematics. Similarly, when you talk about the materials, you should have some idea about the chemistry. In fact, our School of Physical, Chemical, Applied Sciences, where you have the physics, chemistry, and the earth science, 3 departments are there. There are about 60 faculty members. As a dean, I have coordinated with them. Everybody, little bit of contribution that they make, they used to discuss. That has made me to learn the importance of the other allied areas also. It is for allied areas for me. For a chemist, it is his own area, but you need to have knowledge about the physics. Similarly, geophysics or earth science. We have a department, strong department of earth science in our university. These are the links. These are actually given by a physicist, Carl Nave's hyperphysics text. He has given all this information. As a physics person, he feels that you should have knowledge about these things also. It will be useful for us to understand about the connection between the various topics that are there in the geophysics. Even though we are working on a pure physics, physics alone. This is the biological science again, that's also important. So we have done some dialectic relaxation studies on the blood samples. And we have done something on the water. So we can see that blood sample is connected to these biological things, and we try to understand the dynamics which is involved in those things. So therefore, the knowledge of this is also important. And nowadays, my biology slowly mathematics is taking over. So it is necessary to have all this. Usually, one should have this kind of pictures that you should keep it. Now, when it comes to the physics problem, solving, visualizing physics problem, what is the purpose of that? So we have to provide a material medium or the materials for students or beginners, so where they can investigate space-time evolution of the system on a various manipulative parameters, input parameters. Which means you make it working condition to them and make their learning very comfortable by providing the space-time evolution systems on with the variable parameters, and let them make them to learn. And that also provides they gain vital physical intuition via active exploration of the physical conditions. So when you develop such things, we make sure that these two things should be, keep it in mind, so that when they learn through the Mathematica, these two things should happen. Any topic, whatever they learn. So now some of the things which you can think when you start looking at things computational way, looking at the physics problem with Mathematica, there are many advantages. I've listed out here, and you would see when you complete one problem, then you would realize that all of them are really correct. So one is forced to think very precisely. Gaps in understanding must be eliminated if the program is to work. So when you make it program is workable, then by the time you are sure that it's going to be some little bit of gaps that are there that will be eliminated. So one is forced to think very precisely. That happens when you wanted to reproduce the results and see the intricate things that are happening in your physics problems. So you can do dozens and hundreds and thousands of cases can be examined. It's also true. Perhaps new models and phenomena can also emerge. Methods of verifying the results must be worked out. We will be always trying to cross-check. For example, if you say quadratic equation, two roots are there, whether this root is right or wrong, how do we verify? Start verify it, then you will try to understand more about it. So once again, adding one's overall understanding, that's going to happen. Okay, any algebra which you do, you try to cross-check it, whether that algebra is come out properly or not. Various other means. Different proofs of the same theorem can be compared with the point of view of algebraic efficiency. For example, factorial and factorial, okay, can be written by using Mathematica about 15 different ways. Okay, I can check it. Okay, so it's possible to understand them, and then you'll really see which is more efficient. Okay, because it's going to be a big number that's going to be generated. So those things are, one can really, unless there are many situations that even physics problem we try to do. One can examine historically important ideas from the varied perspectives provided by Mathematica. Often we'll obtain a new insight also by doing that. So these are all the things that's going to happen when you really try to do problems with the help of a Mathematica, which is available as one of the most modern tools for doing science, engineering, and technology. So the message from my experience, you can become a good physicist by having certain level of talent in mathematics. This is must. This you have to gain it over the years. You should be fascinated with understanding of the way things work. Continued fascination is important for a long, slow road to your physics career. And by continually learning every year of your life, you can realize these things. You're learning continuously over the year. You cannot master the physics quickly. I don't mean an ability to learn quickly, but an ability to learn correctly. This is very important. You can learn quickly, but we learn really correctly. Once you learn goes correctly, then you start think about that problem and is there anything can be done over that. Okay, so with a bit of skill and talent, the perseverance and an aspiration to learn, with a little luck and the right teachers, so this also should happen in your life and career or institution, you can go much farther than you would ever imagine. So this I really experienced these things in my career over these years. Okay, now we'll come to the real problem of this. Okay, now you can see what and how will you do physics. As our Vice Chancellor also indicated, there is a loop being created here in terms of the observation of the physical phenomenon and improved observation. This is given in this paper. This sort of a chart is given, but is available in this. Now you can see this loop goes on. Okay, continues for a year and years and years and years. And there is a development on experimental aspect of it. For example, resistance, you know, it's a ohms. Now resistance can be written in terms of a fundamental constant H and E. H by E square is a resistance. Amazing thing that happened in the defining the resistance from beginning to now, people are trying to use as H by E square as a resistance. So this is a measurement of a Hall effect. Hall effect will become a quantum Hall effect. So you can see this great thing that has happened in this area of Hall effect or electron properties or electrical properties of material in the presence of electric and magnetic field. And then modeling aspect. See, this modeling is a challenge in terms of understanding the quantum Hall effect. The Hall effect has become a quantum Hall effect in terms of H by E square. And you have the mathematical modeling, mathematical solution, physical interpretation, checking the solutions with observations. This goes together. This loop also growing. It's also growing. And nowadays, I believe for both of them, computers play a major role. You cannot avoid this. Okay, it's impossible to roll out the use of computers. And exercise problems. For learners, this also play a role. And researchers, they also play a role. Okay. So this is sort of a crude way of looking at the scientific way of approaching things. So this is, one should keep it in mind. Okay. So this is growing and this is growing. And I would like to state here the Bernard's statement that the science is always wrong. It never solves the problem without raising 10 more problems. It's true. That's why there is a growth here. But we felt it's only Hall effect has become a quantum Hall effect. Ceramics became a superconductor. This is a great observation. Okay, like this, there are many things that are happening. Okay. Right now, hello? Yes. There's some disturbance. So now there is a question by a student some time back when I was doing my lecture. He asked, "Sir, you are saying there is a cycle. This is going on. Now, what is the final growth? What is the as on date? How much the physics has grown?" It's a question by him. It seems to be a difficult question to answer, but it's a question raised by the student. Then I really felt that it should be answered. So, with my understanding, with referring the all possible text, and finally, I have come out with the result or an answer saying that this is what the growth of the physics E, C, G, H, K. Okay, if you add one more or break this, it's going to be a revolution. Okay, so if somebody can break this or add another one, it's going to be a revolution. I'm sure about it. This is what the growth of the physics. In fact, physical science uses all of them. Okay, physical science, all of them is being electronic charge, this electrodynamics complete. Okay, field theory, whatever you call it, this E is the starting point for us. Velocity of light, G, the gravitational constant, H, Planck's constant. Okay, these numbers, though they are all very small and very big, they are all very, very important numbers, and you get a strong feel if you work more and more towards understanding these things. Okay, so this is what our aim also to understand this, and is there any possibility of making an additional physical constant or break this physical constant? Somebody can come out with this, no, the H is not the ultimate, if something else, then it's going to be a breakthrough. This took at least 120 years back, it has happened. Okay. So now this is the one which is going to play a role, that with this we are going to say that my life becomes very simple and I use this computer with the modern software that is available like Mathematica. And here is another question raised by the students. Sir, how do I understand the quantum harmonic oscillator? I'm able to see the visually, I can feel. Okay, visually I can see and feel the classical oscillator, classical harmonic motion. How do I visualize the quantum harmonic oscillator? Here is the picture which shows, which is developed by using a Mathematica, and here is the answer for it. And you can see all quantum aspects are entered through this. There is a wave packet to locate the position. This wave packet undergoes the simple harmonic motion. And there is an evolution of the wave as a function, as of time, the wave packet evolves, and the evolution can be seen. that evolution takes place periodically, which includes all about the quantization, uncertainty, wave packet duality. Okay, all this has been built in. All fundamental aspects of quantum has been built in. So after showing this, people felt, yes, sir, we could be able to feel that there is a quantum object which executes a simple harmonic motion. And they will get a lot of understanding about it. And that is being observed in several situations in solid state and condensed matter in radiation physics. You see that it's going to be a wave packet and its evolution that can be there. Interaction of our matter with the wave, all these scattering problems all can be understandable. Now, another aspect here, you have a wave packet which is coming from the left and moving towards the right, and there is a barrier. And you can see this wave packet goes and sees this delta type potential barrier, reflected and transmitted, and there is change of width can be realized, and height also reduces. All this that are happening. This is again being generated by using a simple Mathematica. So now we can see the tools that are extremely useful. Now we can see the concept of the quantum harmonic oscillator. I'm able to feel, and student also now he can feel it. Similarly, there is a wave packet which is coming from left. For example, particle from the left with a wave packet which is moving toward that. There is a barrier, there is an obstacle here. That's this obstacles and the disturbance to this, and there is a reflection, and there is a transmission also takes place, and there is a reflection and transmission. Interference can also be seen here. That also can visualize here. Okay, these are some of the details which are available. Some of them are available now. It has been improved large, and the materials are available with me. All this we are trying to do finally to produce a products and gadgets that benefit humanity, keeping the nature intact. This is very important. In fact, the consequence of not keeping the nature intact, we are realizing now. So therefore, it is important that we have to really keep nature intact. Okay, if you don't do that, then we will have a big consequences like what we see now in the entire world. Okay, this is all about it, and we will see how we are going to use this. And this is the person. This is his achievements for the years. How much he has done that can be seen. A physicist, already somebody has hinted that, and at the age of 15 he has made a publication. I have seen his first publication. This is PhD, the age of 20, worked in these places, and he is now president CEO of the That's a great thing that he has done. Now version 12.1 has come out, and you can see the growth of the version 12. Now something like 6,000 mathematically defined functions that are available to do your science, engineering, and technology. You can do all these things. Symbolic, mathematical computation, numeric, visualization, algebraic manipulation, data analysis, graph computation, interactive computation, image computation, geometric computation, audio, all image processing, everything can be done with this. Now I experience all of that. That much I have experienced at every stage of it, starting from 1 onwards to 12. Now here is the typical number which is being generated, pi. The number, pi day. This is March, 14th March, 3.14. 14th March is the pi day for celebrating around the world. This is the number. And I have taken the real digits. Pi minus 3 means 3 will not be there. These are the decimal numbers. And you can generate the numbers. Okay, these 1,000 digits are there. You can have a 10 power 2, 10 power 3 digits, 10 power 4 digits, 10 power 5 digits, 10 power 6 digits. In fact, you can see 10 power 1, 2, 3, 4, 5, 6, 10 power 6th decimal. What is the 10 power 6th decimal in pi that has been found by using this Mathematica with in a time of say 0.04, say 573 seconds? That is the number is 1. Okay, and you can generate any such numbers, and you can find out how many ones are there in this, how many twos are there, how many threes are there. Put them in order. For this 10,000 or 1,000 digits, you can see number of zeros are 93. The number of zeros lying here. Okay, number of 1 is 116. All can be done like by one line. Okay, we try to do that. This is what we are interested to do. So we want to have a capability of the sorter to that extent. That's what we would like to verify and see that whether that can be used, that can be obtained. You can hear 1,000 digits. Number of 9s are 106. I have put in a shorted form. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 digits are there, 0 to 9. How many each one of them are there that can be found within fraction of seconds? I'm able to locate 1 power 6th digit within this short time. This is what pi. And if you wanted to see that, I just created a small program to demonstrate that, to see how powerful is handling these numbers in Mathematica. This is what your number, you can see pi, numerical value. I wanted to have a pi up to starting from 10 digits to 10,000 digits in steps of 10. I'm able to see these numbers. Probably I have to enable the dynamics. Now there is a dynamics, generating the dynamics now. Generating number is the dynamics. Okay, you can see here the numbers. Go on, go on, go on, go on. Now I have generated the 10,000. 10,000 digits are here. Okay, amazing to see such numbers. And you can analyze the numbers. There are very many great things people are trying to do with this Mathematica, with the pi. With the pi, people are doing wonderful things. Okay, I hope I'll be having the next slide showing that, yeah, you can see 200 billion digits that can be analyzed. How many zeros are there? 1, 2, 3, 4 are there. That also has been shown here. Okay, so that is the beauty of that number. And you see the power of the number capability of this Mathematica. Here is the number E. Look at the E. You know, this is an exponential e power 1 is this number. 10 digits of this. Okay, you can generate. This is an irrational number. This is also an irrational number. It goes on and on. I have generated 10,000 digits of the pi. I'm sorry, E. This is never-ending numbers. Okay, and you would be surprised. There are questions. How does it possible to generate such numbers? What is that he is trying to do? These are all the questions which you raise and look for answers. And we are happy with the 3 or 4 digits of the decimals in both the cases. There are just towards understanding these things also. And amazingly, that you can see one number never ends, irrational. Another number also never ends. And you combine with an I, which is square root of -1. And you combine all of them with the +1. E power I pi +1 is going to, so you can see the 0 here, 1 here, amazing pi sits here, amazing I is all there, then amazing E is there. These are all very, very fantastic numbers. And if you try to know more and more about it, you will understand more about the understanding the process. For exponential is the natural growth. Exponential is a natural growth. I cannot have a 2 power n, 10 power x. That's not a natural growth. Natural growth is the natural logarithm, which is, we call it as the natural logarithm E. And how do you arrive this number 1? What makes this number E so great? If I don't have I, okay, here square root of -I is not there, it's completely different. So e power ix, e power x, they're completely different. And this magic comes through the I. And we do a lot of things in physics with this i's. The complex quantity square root of -1. So that through E, we do wonderful things in physics, and we'll understand so much about the physical process that are happening in the natural course of dynamics. Okay, so this is a typical thing which I felt I should show it. And there is another thing also which you can understand how powerful is this source of Mathematica. Here, this is the number. And a small digit game which you can try, and people can understand how important is such software and how much time one can save in our lifetime by having such things. What is the largest number that can be obtained with 4 digits of 2 and no other sign? Positive sign only allowed. And with 4 fours, what will happen? If I have 4 twos are there, this is the first number that's possible with the smallest number of digits. This is the second. This is the third number. This is the fourth, 2 power 22. Then you try with the 2 power 22, 2 power 222. So I'm just looking for the biggest number that is possible with the 4 twos. This is then the biggest number that's possible. Then 2 power 22 power 2 power of 2 power that number. That's the next biggest number. But if I do other way, this I'm just reversing here. 2 power 22 power of that number, because for the 2 power 2, this is the biggest number that's possible. Which I generate, and I would get the number like something like 12,62,612 digits. Okay, if I find, I can do all these things. You can see within no time this will be done, and it will be counted, and it will be listed out. That is what the beauty of this software now. And interestingly, you find we compare with our human capabilities. Let us calculate average human calculation capability. Suppose a person can perform 1 operation per second. The number of possible operation in his lifetime, 17 years. Okay, this is the number of operations. And an average 0.2 seconds of computation time is equal to 1 person's lifetime. Message is that Mathematica, like software, should be explored for innovative work in our pursuit of science. So you can see you are working. If you work for 8 hours a day, 5 day week, 5 day week, and 4 weeks, and 12 months, and 70 years. This is the number of operations that's possible. Now we can see this being done. Now I'm evaluating all of them. You just observe how much time it's going to take for completing the process. Done. Already results have come. Okay, you can see this. Output 9, this 2 power 22 of this 2 power of 2 power 22 is 12 lakhs. That you wanted to see the number, you can open it and see. I wanted to show all of them, or set a limit, or show more. Show more, it is little more added. Okay, if I wanted to see all of them, then set size limit, show all. It's going to be a big number that can be seen here. You can see all the number that you need that has been generated. All the number that are required is available, and it has been folded and has been written here. Okay, so that is the power of the technical software Mathematica. So now this is compact fund is given. Okay, so this game you can try, and you can select. I already given a question. Okay, and with force, what will happen? That you can try and then check whether you have any limitation in the Mathematica or limitation in your computer that you use. So therefore, you should realize that it is really a powerful tool. Okay, this is to visualize your so-called what do you mean by slope of a function. Very many places we will use this. We minimize the function, try to look for the minimum value by taking the derivative. And the digital signal process, this signal with the noise. This is the noise signal. This is the Fourier transform. Okay, inverse Fourier transform. Take a Fourier transform, inverse it, and you'll get back your signal that's going to happen. Whether this can be implemented, yes, it can be implemented. This is the digital images, and you have the power spectrum. We'll show you one by one, and this is some of the simple things which is already available. It has been created here and so. This is the projectile motion, 45 degrees is the range maximum. This is the fluid dynamics part. This is the entropy change, and entropy becomes constant after a time. This is cream in a coffee, which is at higher temperature, and this can be seen. The dispersions of light and the quantum object particles. As a particle is dispersion, which I have already shown. Then this is the self-similarity fractals. Like that you have. Okay, we'll go to some of the interesting things which I already mentioned in the case of using the Mathematica. I hope that screen will be seen for all of you. I wanted to show you this free-fall dynamics. And as I explained, that we should understand it more on that. And of course, this is the great contributors of the classical mechanics and how the classical mechanics are connected to the various disciplines. This is the linear motions and rotational motion. We start from here. I think screen is clear for all of you. Shaheen.
Yes, sir. Yes, sir.
Fine. No issue. So audio also clear.
Yes, sir.
Fine. Okay. Now this is the distance. Okay. This is half GT square. Initial position is 0. Okay. If you make a plot, this is what the curve. This is the displacement as a function of time. Okay. This is half GT square. This is the free fall. This is the acceleration due to gravity because of the gravitational field. This is what we are starting from a height of about 50 meters from here at time t equal to 0, and this is the particular path that is taken by the object, which is free fall. This is what the displacement as a function of time. Okay, this is a t square. This is a parabola, part of the parabola, and we can really understand. If you have a clear-cut picture about the mathematics of the parabola, then you will understand immediately about what is the kind of dynamics we are going to look at as a function of the variable as a time. Now, take a slope of this. Derivative is going to be velocity. That's what here. Fine. and find out area under the curve. Then integrate. That is going to be your displacement. This is n integrated from up to 3.2. That is exactly 3.2. This is what your total distance. Okay, a little more than that for the. This is 50.157, 3.2 seconds. That is what the distance that is being covered by this object. Okay, now I would like to visualize that. Okay, so maybe I will evaluate them, all of the statements, and that will be done automatically. Don't worry about that. So it is evaluated, all the statements are being evaluated. Now I want to look at this is the path and the velocity of that, and the derivative can be seen here. It's going to be a straight line out for this because t square, half t square, when you take a derivative, is going to be t, which is a derivative of that, and you can find out the slope at every point of it. That's going to be your velocity, that will be same. You can identify by looking at the velocity will be how much is the for this one is going to be velocity is 9.8 into t. The slope is 9.8 every point when you are moving on this line. Okay. So now that movement can be seen, and this can be animated and look at. That's the greatness. I can get a feel of what is meaning a function and a derivative, what is happening, and a derivative gives me velocity as a function of time. Okay, this is the displacement and the velocity part of it. Okay, this is animated, and we. What is interesting is what you mean by a differentiation can be understandable. You can change the x by small amount. Okay, for a given function, and find out what is happening to the function after the incremental divided by del x when del x becomes very, very small. So del x starting from 2. Okay, and just created this picture by the method of, we use the mathematical method to find the derivative of a sign that has been done numerically to show that as del x goes to 0, approaches to 0, you would get this sign becoming a cross in the derivative procedure. That is the procedure which we follow. And del x, the limit del x goes to 0, you have the derivative of that. And that can be visualized here. Okay, it's getting matched. Let's say the simple trick to show that it approaches when del x approaches to 0, it goes to exactly to the analytical function what you have. That's the beauty of it. And instantaneous velocity we talk. Instantaneous means at that given point, what is the slope? That can be shown for an exponential function. This is the curve between 0 to 2. This is the value. At this point, there's a tangent. And I'm going to move near to that to just say that from left to right about 0.001, the difference on this side. And see that the point is very closely goes to that del x is approaching to 0. Then you have the instantaneous value of this function, which is we define in the dynamics instantaneous velocity. So now that can be seen. So with this function, we can try with other functions also. Now you can see what's happening to that. I'm just expanding the region, zooming. So let me start zooming and then show you now. See, at the end, I'm having it with respect to the point 1, the curve and the line are same. And you see the left and right, the magnitude is 0.001. The difference between this side and this side, 0.01. To that accuracy, we try to find out. That is what your del x is. If you want, you can reduce. It's possible. And you will end up with the number what you have here. Okay, e power 1 value that's possible to find out by the analysis. So like this, you can find out any curve, what is really the corresponding value of the slope that can be found. Here is the free fall. Now we have seen this by the gravitational fall it is taking place. I'm going to look at the free fall at a different time where is the object is. This is what the free fall emissions can be seen in a 2-dimension. Yeah, I hope you are able to see this and correspondingly where is the particle or where is the object at a given instant of time. This is what your time variation. Okay. Next, stop it here and make it as a 3D object and look at it like a small ball-like structure, and we can see it is going to move now, and we can find out at a different time what is the height. Which means I am able to see in space what is happening with respect to the time that I'm able to observe it when there is a gravitational field. Okay, I'm able to feel that. Okay, so therefore you would really understand what is going in between at a given time. At this time, what is happening? At this time, what is happening? Where it is? What is the location of it? Okay, and what is the kinetic energy? What is the potential energy of that? What is the velocity of that? Everything can be calculated, and these are all responsible. This is all happening at a time, with an evolution of the time. Okay, so this is what your object that is evolving in time. So now we will like to plot the velocity as a function of displacement, and it is the distance that is being. This is the velocity, maximum velocity at time t equal to 0, and then it goes on and decreases when it reaches the height. This much. This is velocity versus d plot. One can clearly see how things get changes. A negative velocity indicates there is a negative. It's coming down. Direction is towards the earth. Okay, displacement also having a minus sign. Now I plot potential energy versus kinetic energy. And we have a straight line, and you can see the energy from potential energy at time t equal to 0 minus 500 becomes plus 500 for an energy for a mass of 1 kilogram. If I take, that's going to be a straight line. At any point of time, the total energy is conserved. We can move on that. At any instant of time, this time is sitting here to calculate these energies. So any instant of time, you can really feel that there is going to be a total energy of the system is conserved. This is free fall, okay? And we can find out what is the exact time by using this also. Because this is what the time taken, what is the height of it, this is the height of it. Now I will generate the numbers for a 5 kilogram and 25 kilogram at different times up to 3.2. Where is the object is? What is the velocity of that? What is the acceleration due to gravity, which is constant, of course? What is the force that is acting? What is the corresponding energies in terms of potential energy, kinetic energy? What is the total energy? This can be clearly seen here that there is an evolution that takes place. And you can see whether you drop 5 kilogram or 25 kilogram from the height of say 50.1576 meters, you can see the 5 kilogram object and 25 kilogram object reaches the height ground from this height to ground in the same interval of time. That is the most important thing that one would learn. Okay, there is a timing evolution, but the different dynamics in terms of energies and the forces. Okay, the dynamics is very great here. The force acting on them also, it changes. Okay, this is a conservative force. Energy is also conserved. And there is a dynamics which goes on with respect to this acceleration. With respect to the time, you can find out in between time, any time between 0 to 3.2, where is the particle, what time, and what is the velocity of that, and what is the force acting on that. With that force, what is the kinetic energy, what is the potential energy. This can be seen. There is an evolution that takes place. And this is true whether you have a 5 kilogram or a 500 kilogram. Suppose you may ask, sorry, if I put a point not on 1 gram. Make sure that there is no other buoyancy forces that are coming. There is no other acceleration that enters. Okay. Then if you want to perform such an experiment with a light object, then you create a vacuum. There is no buoyancy force. Otherwise, you can add the contribution of that in your differential equation or in your equation. What is the consequence of the buoyancy force on the masses, and then modify the equation and look for the solutions. Then again look for what happens to your conservation and the dynamics. So you can see that 5 or a 10 or 100 object where you assume that there is no air resistance contribution. See, the total energy is always conserved. These numbers generated gives a good feel, which is dynamics that is taking place with respect to the time that are all responsible for this thing that is going on. For the gravitational acceleration, the 9.8, which we assume, of course, this can be very minute changes will be there place to place. And this is the velocity variation. It starts from 0 velocity and reaches with this. But you see, with this velocity, okay, the kinetic energy is so high when it touches the ground. You can see this is something like total energy is something like 12,293, whereas this is 2,458. You can see that is almost 6 to 7 times. The impact will be very great on the earth. Okay, when it touches on the earth. So, but energy transformation, all this energy transformation with this kind of a difference should take place within the same interval. Even if you have a 50 kilogram, 5,000 kilograms, the energy will be too huge. Then transformation should take place within the time scale. The dynamics should change in such a way that the force component and the velocity component will be in such a way that you would see that within the same time interval, that energy transfer should take place. So that is what actually happening within the dynamical process. So this is what the free fall, and I have shown it for the different masses. This is different masses and converting the kinetic energy, potential energy, all these things. Okay, so now this is the another way to look at it as a function of acceleration at that time. What will happen? This is what your velocity and the displacement. You know what will happen when you change the acceleration. This is the fixed acceleration, whereas here you are changing the acceleration. Now what will happen to the velocity and distance? When I have an accelerated situation, I will see that the distance covered will be enormous when you change the accelerations. And you can see the slope changes corresponding to the velocity slope. The velocity is different, and distance covered also, which can be possible to feel by just changing the acceleration, having a plot of velocity and the time as a function of velocity and displacement as a function of time. I am looking at the variation of the A, which is possible for me, and the evolution can be seen with respect to the change in the acceleration. This is what in real life we do. When you move on the roads, this is what really happens. Our acceleration changes, and see what is the happening to our velocities and the distance covered get changes. Okay, this is when there is a change in the acceleration. This is what is happening. And of course, we can make a 3D plot showing the velocity as a function of acceleration and time. This is V as a function of A and T in the z-axis. This is the time axis. This is the acceleration axis. And you can see the velocity changes when the acceleration is increasing. That can be felt here. If you are changing the acceleration, velocity goes up. Okay, I'm able to feel all the three at a time. What I have shown here, I'm able to feel it at a time, showing all of them the different acceleration. Here I am showing these two as a function of t, but here as a function of t, I have v is a function of a and t that has been shown. It's an advantage that you have when you have this. And this is being animated as a function of acceleration. But here it is being animated as a function of acceleration. Also there. Here again, this half at square. Displacement as a function of t. The 3D plot again, we can see. This is what the so displacement as a function of a and t. This is curved features can be seen. Parabolic nature can be seen. V is a function of a and t. Here is the T is a function of a and t. These are all options that are available for you to do it. And you can define the function with the initial velocity, initial position, take it up. First derivative, second derivative, automatically algebra is done by the Mathematica itself, and make a plot, and you look at independently with the initial position, different positions with an acceleration. You can see what is happening. What I have shown is independently can be also be seen. This is with respect to 3D pictures showing with a nice motion of the object as it is with the red dot. Okay, as a function of time, this is happening. And the numbers also being calculated and how this velocity changes. It's also being shown. Okay, now there's another interesting aspect with respect to these forces and the potential energy. Del cross F equal to 0, if it happens, then we call it as a conservative force. And when this conservative force is there, the gradient becomes the potential that's equal to 0. This is an important thing that can be learned, and it can be proved for various situations. And if you are good at with this Mathematica, we can very easily cross-check it whether these are conservative forces or not. This is a conservative force. What are it here? This is all about your dynamics that is taking place in the constant and varying acceleration. And this is a good field for us to understand. You see, the dynamically things are happening. The things, the dynamics that's going on, then that leads to energies and the forces. So this table gives an idea. And that's why we want to put the pictures. This is for the classical, well-known study which we have been learning from this school onwards. Now I feel that this will give a deeper understanding about what is really happening in terms of the dynamics. The second part of it I wanted to show, start with the black body radiation. So very interesting aspect. This is the birth of the so-called quantum physics or quantum mechanics, and H is, I don't have to tell the importance of the H. Okay, so this is being executed now completely. Okay, so important experimental observations are, I would just wanted to say a few words about the nature of the black body radiation spectrum and what are the experimental observations to start with and what happens to that when you try to see the black body radiation. So now we can see experimental observations. What are the experimental observations? With respect to the frequency, when you make a measurement of the energy density, okay, you find there's going to be a peak that is being observed for a given temperature. Raise the temperature, you find the peak gets shifted to a high frequency. That's the first observation. It's an universal observation for a black body. Now find out what is the lambda maximum or a new maximum into temperature. This is the new maximum, new maximum, new maximum, new maximum into temperature. That is a constant. It's an experimentally proved fact. There's no dispute on that. Find out area under this curve for every one of them at a given temperature. Divide by T power 4. You will get a Wien's constant. Okay, this is the experimental. These three things are experimental aspects. And there was a struggle which is going on for more than 20 years to understand this and get a proper function. There was a big struggle that is going on, the literature, and there are people like Rayleigh, Jeans, and then Wiens. These people are working on that, and finally Planck has tackled it, and he has come out with a function which can explain all the experimental features of the black body spectrum with respect to the frequency, with respect to lambda, and what are they mentioned in terms of lambda power total area divided by lambda power 4, and then lambda maximum to T. Then Rayleigh Jeans results in the extreme limits, and also Wien's result. All this thing has been produced. And you can see here, when I change the temperature, you can see this peak shift can be seen. That is being accommodated by the function. Okay, it's nicely one can feel, yes, when I raise the temperature, peak is shifting. And you never see these curves, okay, crossing. You expand it and look at it. And what is the thing, physics, which is responsible for such behavior? Okay, which can be realized by quantizing the energy levels, quantize the energies that are coming out. This is smaller energy, this is higher energy. Smaller energy, smaller probability, higher energy again less probability. In between these two, there is a function which is taking care of this peak that is being observed. So this is lower energy, this is the higher energy. The photons that is coming out, this is produced by this named by chemist, and these photons have a lower energy here, lower probability, higher energy, but still lower probability. The nature of the function is such that it takes care of that, so becoming a smaller value on the higher frequency and lower frequency. At a given temperature is going to be peak. When you raise the temperature, this is happening. What is the function that takes care of such behavior? That is what given by our Planck's radiation law. That's what is given by him. You can do it for both the case in terms of the frequency and also in the wavelength. And you would understand all about it. See, this is the lambda maximum determination. Okay, very easily, as I said, now you take a derivative. You can see this is what your normalized function of the black body radiation, and this is what your slope at the point. And when I change it, I will locate where is the maximum is lying. When it crosses the red line, the dot which is crossing, slope is parallel to that. That happens at a particular point. 2.82144, the slope becomes 0. If you want to enter that, you can enter it 2.82144. If I enter, that's going to parallel to the x-axis. So to 0 exactly at this point. Okay, lambda max can be fixed, and that is substituted back, and you'll find out what is the lambda max. Is it in lambda x, which is in frequency? Mu maximum has been fixed, and this is what the number that you'll get. Similarly, see, this is the problem now. It cannot be solved unless you have a computer. Okay. So those days, people have come out with the calculations with such an accurate value. That's great at those days. Now it is just done within a one small program by writing some few lines, I mean, we are able to, but those days, in fact, when I was doing my computation with the Fortran, now we spent a lot of time to find out this slopes and equal to zeros, all this, everything is done now automatically, found, solved, and this result has been given. That result has been, visually we are seeing it now. Okay, and this is with respect to the lambda. And you can see the constant is something like this. This happened. This is what your curve. Okay, when it reaches this point, so which means you substitute the value of the number equal to 4.96 511. If I substitute and enter it now, enter now. Okay. This is parallel to this, but the number has changed a little bit. 4.9. You can have an accuracy of any extent. 4.96 511. Enter it. This is parallel x-axis, exactly 0. This decimal accuracy. In fact, I have shown this accuracy. You see, it's not an issue at all. 100 digits of accuracy you can evaluate. The precision can be changed, and that root can be found to any extent, because this might be required, because on with respect to lambda, this is an angstrom. Therefore, you need to have an accuracy of, say, about 8 to 10 digits of accuracy to get a lambda max accurately to find the lambda max to T. So now we can see what is being done here. It is quite interesting to look at in terms of the parameter with the physical quantity, what is associated here. See, this is what your number of modes that are there. As time evolution of the modes can be seen here nicely. This is the first mode which is evolving. Okay, I'll increase the number of modes by changing the k value. This number of modes are changing. I'm able to feel this is what the modes that are there. Okay, and I can change the speed of this mode by changing the frequency, faster, faster, and faster. And I can change the number of modes. You'll get a feel. What do you mean by a mode? You don't understand, but you can visually feel, because black body has within this cavity you have the modes. That modes are established and has been shown that is varying in the frequency proportional to nu square, and in terms of wavelength it is by inversely proportional to lambda power 4. What is this number? What is this quantity? This is actually number of modes per unit volume per unit frequency interval. That is what the unit says here. So when it is written, immediately you should come to your mind there is a number of modes that are there in a unit volume per unit frequency interval. If there is a d nu interval is there, then the number of modes that are there in a d nu will be nu plus d plus nu, nu plus d nu. That's the greatness of this when I split and write like this. Okay, this is the classical result. Energy has been taken continuous. This is kT. Okay, now you have the, with respect to the nu, this is what the result. Okay, classical result. Energy density, the distribution is, this is the form. With respect to the lambda, you see, with respect to the, after finding this unit becomes joule per meter cube per unit frequency interval. Okay, energy density per unit frequency interval. So this means, okay, energy density per unit frequency interval. Come to the next one. This is the number of modes in terms of lambda. This is the transformation that is done from nu to lambda. Okay, this is number of modes per unit volume per unit length interval. This is in meter. And in terms of energy density per unit length interval. So this is, once you understand this and this, then it will be easier. And this is the energy of the average mode. KT is the average energy of the mode, which means I'll find out what is the total energy of the modes and the total number of the modes. Divide that, we'll get average energy of the mode. That happens to be KT. That is what the result that you have classically. And that doesn't work well. There are a lot of issues on that. People have spent time. Finally, our Planck has cracked that by replacing the energy what is being integrated here continuously from 0 to infinity. This is what your distribution now. Okay, the modes distributed like this, e power minus energy divided by kT. This is the energy, the average energy of the mode and the total number of modes. Average energy of the mode can be found. This is the total energy of the modes. Find out the total number of modes, divide that. That's what you are getting. Now this is done quantum mechanically, and that energy has been here. This is kT, and this is what the happening with respect to the quantizations. Now you start look at the entire thing through this distribution now. What is the average energy here? The distribution is like this. This is what your distribution now. And this distribution, as I said, the lower value of energy, less probability. Higher value of energy, because of energy difference is very large, is going to be less probability. In between lower and higher, there is going to be a peaking. That is what being observed. And that is what's the success. Now you can see the same unit is here, same unit is here. But what is happening is H that is being introduced here. And that H is playing a crucial role. And with that, the whole thing has been analyzed to get the Wien's constant and the Stevens constant. That all known as in the textbook level. Now this whole thing has been done here. Now we have made a plot, and this is what the result that you have. And you will feel very comfortable. Yes, I'm able to get an idea about what are all things that are happening with respect to the variation of temperature, frequency, and you can see high frequency shifting, and here it is flowing. The peak can be located here. You can see I have made a three-dimensional plot. Frequency shift can be seen from a low frequency to high frequency. These are the peaks. It gets shifted here in terms of the plot, and I'm able to feel that by looking at. You can see the shifting can be seen. It's an amazing thing that's possible with the help of this. And what I said is, at lower energy, this is what the result. Higher energy is this. This is in the last scale, so that you can see the entire range, covering from 10 power 11 to 10 power 15. And higher energy means separation is more, less probability. Smaller energy, because of HU is very small, there's probability less. But in between, this is what is happening. There is a reasonable probability that is there for the distribution. That's what we seek. So we could be able to get a complete feel about, in terms of the photon energies, how things have changed, or the energy of the radiation that's happened. And you can find out what has happened to these scales. Nu with HU by KT numbers, generate the numbers, find out what is the energy value, plot them, and this is with respect to the lambda. Nothing great here. And you can get these results of others what have been given. And this can be connected to your Planck's length, time, weight, and temperature. Amazing thing that can be happen with respect to the what are the mentioned physical constants that I have mentioned already. 4 of them are sitting here. You can see here, this is the Planck length, Planck time, Planck mass, Planck's temperature. There are yet to verify. People are struggling to find out these things. Is it possible to make that this will become a fundamental quantities again further? And that can be connected. I can get this. You can connect this lambda LP, which is Planck's length, Planck's mass divided by Planck's time. I'll get the Planck's constant. Like this, your other parameters can be obtained. Okay. De Broglie wavelength through this units can be found. Compton wavelengths can be found. Okay. And then velocity of the light can be predicted. So there are many things that are possible with these quantities, what is defined in terms of the Planck's length, time, weight, and temperature. Okay. So this is what has been done. And numerically, I have evaluated them by taking a particular set of data, calculate and find out precisely whether that H is coming out properly or not. I'm able to see that it comes out so nicely that this number can be produced accurately. This is what the number after analyzing the data. Okay, lambda max has been found. Similarly, nu max has also been evaluated. This is the position of it. These are the analysis of the data, and with respect to this, lambda max numbers can be generated. There is a generation of this with respect to nu max with respect to the radiation of this. What things that happen. Okay, this is the second part of it, which I felt I want to share. That there are many other things which interesting is here. Nu max and lambda max are not matching with the velocity of light. I do not know still. I'm looking for what could be the possible reason. Nu max and lambda max, when you multiply, I'm supposed to get a velocity of light. but that I'm not able to get it. There's a difference, and there are points people have raised it, and at that point it is left because the area under the curve divided by t power 4 gives the correct predictions on both lambda and the nu, whereas the lambda max and nu max, there is a difference. There is a factor of 1.75978. This is the difference. It is the challenging thing that one needs to assess this and try to understand more about that. Of course, people are not bothered for it much. I don't see any, very rarely you see the textbooks providing this. There are some textbooks here. So this is what I would like to share with you about the black body radiation, of course. So there are other things. We can look at the solid state matter in terms of Pranipini medal. You have a periodic potential, A plus B is getting repeated, and minus B. You use the block condition, block periodicity, you bring it here, match the wave function with the Bloch's theorem, and solve this. These are the determinant. And you can see algebra, how fantastically it handles. This is the symbolic algebra completely. I started with the wave function at A and B. Match the wave function at 0 and A and B with the Bloch's condition, and you would get these two. And you make a determinant equal to 0, solve that, and you would get the result, and I have plotted here. Okay, this is a simple plot is equivalent to this something like a sinc function, sin x divided by x life. That is what the result is. So it boils down to a very simple equation. That is what appears to be very complicated here. You can do an approximation and show that, and you can see the existence of gaps here, and gaps can be varied with respect to the parameters, and with two different parameters. So the energy band, which I change the A and B parameter a little bit, and then there is a change in the gaps that are associated with that, and that gaps can be clearly seen by plotting this, the textbooks form whatever is given, and you can see this is allowed and forbidden. That can be also be calculated. This is the allowed bands, the forbidden bands. This is the forbidden one. Put them together, you can see visually I can feel the band formations can so clear, and there is a width change also, can be clearly seen. Quite interesting look at this. When you evaluate, you will understand all about it, plus you have a clear-cut understanding about how this boundary condition works, how the Bloch's theorem works here, okay, how mathematics is being handled through Mathematica, that also can be seen. You can see the evolution. Now I evaluated this within no time. It's done, started, okay, done, already completed, okay. So this is what the thing that I felt I should share with you, and there are many such things that can be done in solid state. Okay, before I go to this, there is a gradient issue. Is there? Yeah. So this is a hydrogen atom. Entire hydrogen atom problem can be done. Very nicely it can be done. Evaluate this notebook. Okay, symbolic things. R theta phi. Define that, and what are textbook derivatives written, you just do it systematically with the help of Mathematica. And you have a fantastic result to see every one of them. These are all the orbits, okay, SPDF orbits. This is the spherical harmonics. You will feel it now. Okay. This will take little time. I have not given this plot. You can make a cross-section density plot can be made. That will also be interesting. Okay. So this is about the complete algebra has been done through the Mathematica. So radial part has been solved, and you have a spherical harmonics completely solved. And we have cross-checked the results, and the results are reproducible. What is given in the text can be possible, and you can really feel them and see that things are coming out properly, all the orbits. You have SP, D, F, G, H, whatever you want, you can go further and see them. There's no limit on that. Just change the function, the numbers, what you have here as a variable, and you would get it. Now, I just wanted to show you this gradient. I felt that I wanted to share with some of the simple things like waves. No, if you wanted to how waves are evolving. This is your wave which is plotted minus 4 pi plus 4 pi. And then if I wanted to see its evolution as a function of time, this is what your simple evolution. This is what your starting point to learn. I shown the waves which are whatever. Started moving. Yeah, it's just moving. Okay, this is an one-dimensional wave. And it's not here. And let's come to the two-dimensional wave. Okay, you can see how it's evolving. This is just made r equal to x square plus y square. And your sine cos add that, and it's traveling with the particular velocity. And you can see how this is evolving. Okay, this evolution can be seen. The evolution of that. So nice to see that you can understand about how the waves are produced in a two dimension and how they are propagated with the times. They can change the velocity of that, change the wavelength of that. Now, if I add two closely lying waves in terms of wavelength, okay, and you see the interference pattern. You see the pattern? Same problem, but what I will just small variation with respect to it. You can see that one of the parameters 0.1 and the other one is how much is difference? A is 12 lambda 2, mu is 3. And R1, this is R1 and R2, and this R1, R2, this slight lambda is differed by a small magnitude, R1, R2 differ by a small magnitude. Plus minus 3. So that gives this kind of a pattern. Okay. So we have seen the cavity wave. This is also a wave which is interfering. There is an interference pattern that can be seen. Okay. And you can stop it anywhere, you can see it. This is the, of course, the beats or whatever you call superposition. Adding the waves closely lying, you have the beats that can be seen, and it is evolving. Right? Okay. The evolution that takes place. You can change the waves or frequency or the lambda of the wave, especially if this is the wave which is traveling in opposite side. Change the direction of the wave and they move in opposite direction and they may collide. Okay, or you can make a wave packets and collide each other and they try to see when it is colliding what is happening. So that's possible to generate such things. This is simple things that can be learned from the waves. The derivative I have shown, digital image processing. This is again interesting thing in terms of the Fourier transform. This is the e power minus x square minus y square. If you take a Fourier transform of e power minus x square y square, it's also again come in the form of this one, and there is a change which will be controlled, okay, by changing the Fourier transform. Now this is the numerical form. We generate the numbers, add some noise into this, some periodic noise. Then look at the evolutions, or just see how do I suppress that noise which is coming through this. I don't know what happened to this. Evaluating now. Oh, sorry. Evaluate the notebook. Done. This is the after taking the this is the function as it is. Take a Fourier transform and it's getting converged to the center of it because the width of that Fourier space will be different. And they expand the region of the center portion to look at things, and you can see the both together. This is the Fourier transform in a bigger region and bigger small region which you are trying to look at it. Now there is a periodic noise that is being added. If I take a inverse Fourier transform of this or Fourier transform of this, I can pick out the noise which is added as a periodic noise. This is the periodic noise gives two spots in the Fourier space. I found the space. I located this. Then you eliminate it by making it located. Make it as a. I just suppress this. Bring it to the same color as this, which means you are making it as 0. Then take an inverse Fourier transform of that you would see that the signal has back again and put both the noise and without noise. It's quite fantastic to demonstrate how this Fourier transform works and how powerful is this shortcut to do things and to understand about the simple mathematics which help us to understand the image processing that is happening in the digital form. Okay, now I have, this is with the noise which I have already shown to you, that I'm just showing you again with the computation. This is the Fourier, and Fourier can be understandable. Numerically, one can do it also. Evaluate this. You can see there is a noise here. I added the noise here. This is the signal. Connect them. See, there is a jiggling around this signal. Take a Fourier transform that has been located here. Then bring it to the center and take a inverse Fourier transform. So that jiggle has been disappeared. The signal has been picked up. So this is what your Fourier technique does. And you have an FT. The IR has been FTIR. Earlier it is IR. And you have to become FTIR. Okay, so what is the FT does here? I have two signals. For example, here, one is 400 is one signal, another 400 wave number. This is 450 wave number. There are two such motions are there in a given medium. Then when you take a Fourier transform, when you combine them, you will get, the signal will get combined because of the addition of these two. Okay, when that is there, when it is both the wave numbers are together, you get an interferogram. Take a Fourier transform of this, and you would get both the signal here. Okay, you can see here 400, we expand it 400, 450. Okay, zoom it and put it along the dot and show. This is what the actually Fourier does. That's what your FT role in your IR spectrometer. So if you have n number of such things, for example, 5 of them are there, 5 will be interferogram will be constructed for all the 5 by the experiment. Take a Fourier transform of that, all the 5 can be resolved. That's what is being resolved. This is for a demonstration purpose has been developed, and there are very related questions has been given. If you try to work it out and understand where are the parameters, you will understand all about how this Fourier transform spectrometer is working and how this Fourier is playing a role in the FTIR instrument. So it's possible to get an idea about the role of FT in your spectrophotometer. This is your, as I said, it's gravitational motion under gravity, which is projectile. And this is what your projectile motions, and probably you can see here, maybe enable the dynamics and see what's happening with respect to the time. Well, you're supposed to evaluate the notebook. It's done now, it's evaluated. And this is simplest thing to learn. Okay. What is the angle of projection now? It's 20, and look at the range. This is what the range you have, and I change this. So I keep it up more and more, and when you reach 45, maximum range. The beauty is, what will happen if it becomes 50? So it has to spend more time in the space so that the range covered will be less than what you observe in the 55. You go further again. Okay, this all numbers can be generated and plot it and animate it and show it to the people that this is what really happening. And that's such a simple statements which helps you to understand about the projectile motion in a simple way. There are many such things that are available. Power spectrum here. What is a power spectrum? Okay, I have signals. Two signals are here. What are the signals now? 35 frequency with an amplitude 7. E is the amplitude here, 25 is the frequency that is being combined here. This is what the signal. I cannot make out anything from this. But if I do the so-called the power spectrum analysis, I can pick out what is the frequency and what is the amplitude of that. Okay. So when you learn about Parseval's, I don't know what is the name that is given. Parseval's theorem? No, not Parseval's theorem. There's a mathematical name associated with this power spectrum. So you will evaluate now. See whether you are able to get this numbers. What I have 735, 325. That should be available in the spectrum. This is 325, 735. It's available. So you can understand about what do you mean by this so-called power spectrum and how it can be handled and how it really helps the signal processing and signal analysis. And I'm able to get it exactly what is the amplitude of this and corresponding frequency, which means higher amplitude having the higher frequency. The lower one has a lower frequency. You can change these numbers. You can really do it again. See, for example, I do this small repetition again, same thing, which I do it for a 15 and 20 and repeat the whole calculation. Check whether it's going to work. Evaluate the notebook, yes. Evaluate the notebook again. See, the spectrum is different. You can see that's being observed here. So this is what's going to happen. And these are parameters variable. You can understand how this is being done and how mathematics is being converted in this form to get this interesting results which we use often in our physical problems. Okay. So this is superposition of waves additions, and I think I am supposed to spend some time on these barriers and wells. I hope another 5 minutes time. Shaheen.
Yes, sir. Another 5 minutes.
Another five minutes time. Just close it.
So can you show the tunneling also, if possible?
Well, I just check. That's what I'm coming to the bound state, potential wells and barrier. See, the wave packet already I showed now. That itself is a tunneling again. See, this is the potential well. Okay, and of course it can be converted as a barrier also by changing the sign now. Okay, instead of now, this is the potential well which we have, and you have the wave functions corresponding to that, match the wave functions, solve them for the parameters what you have. Okay, find out what is the reflection transmission coefficients. Okay, incident, reflected, and transmission coefficients can be evaluated, substitute them, and make a plot of this, and then plot them. You can see the region 1, region 2, region 3. I think I should have taken that again. Tunneling, I missed it, but so this is exactly the same problem. Just change the barrier and repeat it. It's not something difficult to get it. Right now, I think I have missed. I think I have put it somewhere to show you that. Sorry, that I have to evaluate this now. You have been asking for the tunneling problem for quite some time. So now you can see it's evolving in time also. Evolution also can be seen here. And 3 different regions, and depending on the energy, it can be a decay solution or another state solution. Okay, that's what will happen here. Maybe the tunneling issue. I think I should have taken that program to show the tunneling. So one thing I can do is to get that immediately. I have to go to the website. I don't want to miss that. Okay. So maybe in the next slide, I'll just check it. Next program, I'll just check it. Well, and this is the bound state problem. Potential well and barrier, black body, potential step is here. I think I have not really made that in a proper form of the tunneling. So this is again for potential step, and you can see that when it is depending on the energy of the potential step and the particle energy, either you can have an oscillatory solution and a decay solution. And if we add another on the other side of it and look for it, then it's possible to get a tunneling process. See, tunneling can happen. Okay, on the other side of it, I can give you the physics of that. How does it possible for an energy of a particle is less than that of the barrier? Finite probability of finding a particle on the other side of it is the major thing which one should understand. Question is clear for all of you? I'm having a particle which is coming from this side. There is a barrier. The energy of the particle is smaller than the barrier, but there is a finite probability of finding a particle outside the barrier. How does it possible? This is the question. What is really, are we breaking anything here to say that classically it's not possible? Okay, when the barrier energy the particle energy, if you compare it, the particle energy is smaller than the barrier energy. Classically, it is impossible to see the particle or object on the other side of it, whereas quantum mechanically it is possible. Okay. Even if it decay, there is a finite probability. Even with an oscillations, it comes out, they can decay. Okay, that can be seen depending on the nature of the solution that you are looking for. There is a finite probability that has been protected by the uncertainty. You know that del E del T of the order of h cross. Okay, over a certain interval of time, within the limit of h cross, the energy is greater than the barrier. That condition is satisfied. Therefore, within that limit, there is a finite probability of finding a particle on the other side of it. I hope this kind of explanation will be giving a strong feel for it. The tunneling. I think you understand what I'm trying to explain. Say, there is a del E del T which is limited by h cross. Okay, we cannot predict exactly del E and del T. So over a period of time where within the limit of h, there is a very possibility, there is a possibility of having a higher energy than the barrier. Therefore, there is a finite probability of finding a particle on the other side of it. So this is the sort of an explanation which gives some convincing answer that there is a possibility of finite probability on the other side of it. Okay, so that is possible to observe finite particle on the other side of it. That has been used to make a device. That's what your tunneling electron microscope. Okay, so that's what the thing that is there. I think I don't have the tunnel problem which I have not completed because I assumed that things are pretty easier to develop and I didn't do that one. You can do it also. It's possible. It's not a difficult thing. You can compare with the barrier energies and the particle energy. If it is less than that, this is what's happening. Barrier energy, otherwise it's decay. And then outer side is possible. This can be explained by using within the limit of uncertainty between the energy and the time. That's how we look at the issues. Okay, I think probably we can stop here. We can take some few questions if you want. And 1 minute. I'm time dependent animation of this, which I have shown you, that can be available here. It's a program form, it is available. Okay, and that is what is being animated here. Okay, this is what your quantum harmonic oscillator, and you can have a classical harmonic oscillator and quantum with respect to the energy states. So these are some of the interesting things I felt I wanted to share with you people, and I felt that gradient, the electrodynamics part somewhere I gradient in understanding. Yeah, this is the problem. Yes. Now, what do you mean by this gradient? Derivative, gradient, and there is a problem connected to this. It's quite interesting problem, which is given the Griffith. You can take this problem, work it out, and this problem can be visually seen. What do you mean by a gradient? And it can be shown in the form of the vector fields. Then you can find out what is the magnitude of that. This is in the form of a vector field gradient. And this is the plot of that, and it can be plotted. And you can see this function has the slope having a maximum value at -2 and 3. X is equal to -2 and 3. That's where somewhere here we can see that location is here, -2 and 3. This is where the maximum point which is lying by gradient. I'm able to pick out for the maximum value which is here, and you normalize and plot that is again -2, -3. This is the point which is the magnitude of that. Okay, gradient magnitude is found, and this is both together. And different function which has been plotted here. This is the gradient, this is a scalar converted into vector. Look at this plot, and you can see, you normalize what happens to that. This is -xy. Take a gradient and plot it. You have, and you normalize and make a plot. This is the divergence. Divergence, how much is being diverging. It's an interesting physical quantity. It can also be realized here. For the function, it is the divergence from the center of the arrows. So the arrows are indicating the divergence. For the function x, y, z, there is a finite divergence. And there's no divergence here. Divergence 0. Then you can find out the divergence for these vectors V, A, B's, and then make a plot of them. Or you can find what is the divergence. Yeah, you can find out divergence of all these things and make a plot and show whether this divergence finite or not. And this is the velocity gradient that can also be shown three-dimensionally. And this is, of course, the delta functions, and this is the delta function, which this is your curl rotations. This is your rotation. You can see that in minus y x, 0, if you find out the curl of that, it's going to be rotation along the z-axis. This can be seen as a finite value of curl, which is in a particular direction. This is again for the function. The curl is this 0 minus y minus z y. This is the curl. Then you have fundamental theorem of gradient and fundamental theorem of divergence and fundamental theorem of what is called the Stokes theorem, which uses the fundamental theorem of curl. That can also be verified. One can visually see what has been given there and feel the actual plots and evaluate them empirically and then explain to the students that they can have a clear-cut picture about what is really happening. Visually on feel. So this is quite interesting. And based on this dells, you can do many operations. All those operations can also be evaluated. Okay. Fine. I think we can have some few minutes for discussion. Then
Yes,
we
sir.
can close down for another 10 minutes. You can have some discussions, questions.
Yeah, yes, sir.
You're most welcome now.
So, if someone wants to ask questions,
Yeah, then they can
unmute
people
them.
can ask some questions. Before that, I wanted to just bring it to your knowledge that some of the research-oriented problems, things have been done.
Sir, we have
Advanced
to,
level programming has been done, and I wanted to show you that this is the course that has been done, just completed about day or two before. Okay, yesterday this completed 22nd, and some class I have taken. This one full-fledged course for 48 hours or 32 sessions, 48 hours has been done. There's another course which has been done before that, Mathematica, as a course. I think some of the participants might have attended already. They have attended that. And now there is a plan for me to start Mathematica in classical mechanics. We'll go from mechanics to classical mechanics. They're all about this Mathematica will be taught, and then try to understand the whole about the classical mechanics, which I'm planning to do. Those who are interested, they can register it. Of course, some nominal registration will be there, and it will be done for a period of, say, extended period of about 4 months. 32 sessions will be there, 90 minutes duration. And it will be done from the time 8 to 9:30. That is what some of the people requested. And it is in PM, it's not in AM. So this is what the plan to start at this time, and not exactly this time, sometime around this June. And it may go up to September, covering the part of Mathematica plus how do you understand the classical mechanics of Mathematica. So whoever is interested, they can contact me, and I may be putting this up also to the people. Okay, and this is what the summary of it. You can really feel whatever I explained. This is what the summary, which I already explained. That you will really gain a vital physical intuition, okay? Very active exploration. Then we are investigating the space-time evolution of the system with the various parameters, manipulative parameters, and this sort of computation has strengthened our many things. Okay, and this powerful tool should be explored to solving and visualizing these physics problems. Okay, stop here. Now we can have some questions. I'm happy to answer some of the questions. Okay.
So, Vinod sir, can we have a couple, 2-3 questions?
Sure. Right, 2-3. You can go a little more also. Another 5-10 minutes, you can have discussions.
So, whoever want to ask a question, they can unmute their mic and ask, please.
Sir, good evening,
Yes.
sir.
Yeah, good evening. Maybe you can tell your name and where. Where are you?
Sir, I'm Satyabhama Ramanuja, Madurai Kamaraj University, PhD.
Great. Very good. Okay, fine.
Sir, I have to do 6-dimensional integral in Mathematica. How to do, sir?
6-dimensional integral, you have all variables available now.
All
Functional form
variables
is
available.
available, analytical, and it can be done. It's not a big thing. It's not an issue at all. We have all variables now.
Sir, I'm not
Which I
familiar
haven't-
in Mathematica.
Okay, but
I don't know basic things
three-dimensional
itself.
things when it can be done, 6-dimensional also can be done. But all it is coupled form.
Yes, sir. Yes, sir. Modulus. 6-dimensional integrals inside modulus will be there.
Okay. I'm happy to send me that some details. Because I have to learn that also. I'll be happy to learn that and work out the possibility of. Yeah, there is in principle it is possible. It can be done because you can do one by one, and it can be completed all the 6 integration in a connected form.
Okay, sir. Quantum optics. My topic is quantum optics. So,
which means you have a K-space and radius.
Yes, sir. Yes.
K-space and
Yes,
R-space,
sir,
is it not? Yeah, I understood. Yes. You have a Kx, Ky, Kz, and you have a X, Y, Z.
Yes, sir. Yes, sir. Absolutely.
Yeah, it's possible. Yes. Possible. You can think about it.
Can you help me, sir?
Yeah, you can send some detail. You can interact with me.
Okay.
And we can try. I'll try to help you to possibility of sorting out that issue.
Okay, sir.
Right. Yeah.
Thank you so much.
But you should learn. That will be interesting aspect of Mathematica. You should learn. Things are very handy. I think you would understand by now. Very, very handy.
Yes, sir.
Very subtle things that are not in a position to learn, you can learn it by using this software.
Yes.
Other questions, please.
So, people already must be tired of this.
Started from 2 o'clock.
Yeah.
Hello, sir.
Govindaraj, sir.
Yeah, yes,
Hello.
please.
Sir, myself Vidya. Sir, I wanted to know about your course on classical mechanics.
Yes.
Like to study classical mechanics concepts using Mathematica. Sir, will you teach from basics or it's like directly you will?
No. I'm going to start from fundamentals. Newtonian onwards. You start from Newtonian mechanics. Slowly
No, sir, I'm like, I don't have any basic knowledge from Mathematica. So I was asking whether you'll teach
parallelly. Mathematica will be explained thoroughly. Okay,
sir.
Given a problem, select it. What is the mathematical is there? How to use that Mathematica to solve the problem. By the process, Mathematica will be learned, and also you learn about the classical mechanics things.
Okay, sir.
So it cannot be done without because it's not possible to learn things like that. So you should have parallelly learn little bit of or reasonable extent Mathematica should also be learned. Okay. So by that process only you will pick up things, and you should in a position to solve to start with, for example, harmonic oscillator problem. Okay, simple harmonic motion. You know the problem, how to do it. Only thing you have to learn the mathematical aspects of it and do it. Then if it is a non-linear harmonic oscillator, what will happen and how to handle it. And if I do it in a Lagrangian form, what happens? Hamiltonian form, if we do it, what will happen? That is next level. Correct?
Okay, sir.
Yes.
So next question, please.
How to make a animated video?
Animated?
So
you mean animation already there in the Mathematica? How to bring it a video form? You mean this? For example, this is
make an animation.
Okay, this is the animation, now. You're able to see the animation now?
Yeah. I
You
want
can
to.
You can learn it. You can learn it. It's not a difficult thing. It can be learned. You can learn that animation, transfer the file to the way you like it, and you may. This is the GIF file. Okay, it's possible. Mathematica has an option to create such options, create such files that can be taken. Right?
Yeah, yes, sir.
See, this is also another animation. You can see the measured experimental data of the dielectric constant as a function of frequency for different temperatures. It's being animated for two different systems. So you can see that's changing as a function of temperature, how it shifts. So this is also an animation. That's what he has explored all possible things what a physicist requires, or a science person requires, or a technology person requires. And it is up to us to take it and explore it and bring it to the form the way you like it. That's how this mathematics has been developed. It's a question of learn and cross that barrier of learning. Once that happens, then you will be master in your subject. I'm sure that will happen, which I experienced personally. Very much I experienced. So, fine. So we can include back.
Any more question from the audience?
So people can interact with me. They can send mail if
Yeah.
they are interested. Then have some
Yes, sir.
learning that can happen over this period of time. Anything when you learn, it has certain barrier. But unless you do it by yourself, you cannot appreciate. You cannot enjoy. Sit and work. Physics is like that. You have to work. Take some sort of craziness to your work. You should really spend your time and learn. And once you go a certain limit, then you can't keep quiet. In fact, you will always try to do something on your research area. Right.
Sir,
Yes.
since there are no more questions, we
Yeah,
can
right.
wind up.
Okay, you can conclude.
It is, yes, sir. It is really a wonderful session from your side, and
Good.
we appreciate.
So how many participants were there finally?
Started it is 210. It was right now when you concluded it was 100. That means
even now 100 means it's big. Great.
Yeah, yes, sir. Right now it is 97.
Fine. That's great. Yes.
Sir.
Yes.
Sir, how to
please.
contact through mail or group?
Through mail you can send me. I have given an email ID now.
Yeah, we have a group right now. Right now we have a group, and
you can interact with a group of our people here. My email ID is here, and you can see it in the slide.
I can share you as well if you want.
This is a GG dipole. It's very easy to remember. This is very research area in which I'm working. I associated my initial with that. GG dipole.
Okay, sir.
It's very easy. ggdipole@gmail.com.
Okay, sir.
That's very easy to remember.
Yeah,
you
sir,
can
how
find
much dimension allowed in Mathematica? N dimension.
It's the limitation of your computer. There's no limitation in Mathematica. If you have a matrices, no?
Yes, sir.
Okay. It can handle a matrices of say 1000, 10 power 3, 10 power 4, 10 power 5, 10 power 6 columns and rows. Okay. I have already shown the power of this Mathematica by calculating the numbers.
Yes.
It can handle any small number, any big number, any sort of a dimension. The limitation is your computer. Okay. Higher the computer, higher the dimension it can handle.
Okay.
You can do wonderful things with the data analysis. Okay. Data analysis, data science can be done very, very beautifully.
Okay.
Which I have done for my research work, handling the data with this Mathematica. That's nice.
Hello, sir.
Yes.
Please.
Sir, in case tunneling, so
is it possible that the classes be taken on Saturdays and Sundays instead?
As it is, no, that's the problem because many of them are working. Okay, working people this is at night time. Please note that it is 8 to 9:30 p.m.
Yes, sir.
It's convenient time for those who are working also. Because many teachers are showing interest, so therefore I should accommodate them also. That's why I'm taking Wednesday one weekday and Saturday one day.
So if it is Saturday, Sunday, we don't have get time for preparing the in between.
So it would be better that Wednesday evening time, 8:30 to 8 to 9:30, and Saturday, so that the weekend at least we can relax, and only one day in the week you have a class for about 1.5 hours. So other Saturday, Sunday is rather difficult for others also. The Sunday at least people should relax.
Okay.
You are working? Are you a student or working somewhere?
No, sir, I am a student.
Student means it's not a problem, no? Okay.
Yes, sir. It's okay.
Okay. Fine. Yeah.
Shall we wind up then?
Yeah, you can wind it up now.
Sir, it is really a wonderful session. We got new areas of physics by mathematics and visualization. It is really, we thank you once again for the all of us present here. Thank you once again, sir. Thank you.
Okay, thank you for
And
all
we will be
this.
in touch with the groups and the mails. If you have any
Yeah,
doubt,
please do that.
yeah.
I thank all of you for patiently listening my presentation for a period of say 1 hour, 45 minutes or even more than that. I thank all of you.
Thank you, sir.
Okay.
Shahin,
Right.
do GT Enterprises person is around and he want to make any announcement or something?
Please let him make an announcement.
If I don't know, Shahin.
Shahin?
Shahin?
But he can announce now. People have left, all of them are.
Okay, okay. Then I saw there is a Mr. Pradeep in the list earlier, so I don't know.
Yes, sir. Very good evening.
Okay, please.
Please.
Myself, Pradeep here. I am from
Okay.
GT Enterprises, Bangalore. We are authorized technical and sales partners to Wolfram for southern states in India.
Yes.
So it was our privilege to associate with you all for this webinar. And really, it was a great session by Dr. Govindaraj, sir.
Fine.
And participants, do feel free to let us know your queries, or if you want to evaluate
they
our
can all
tool.
contact you.
Yes. So if you want to know more about the Mathematica tool and about the licensing, so please do contact us. You can contact Dr. Shahin sir and also us. So we are on the WhatsApp group, so you can post your queries there. We'll be happy to support.
That's fine. That's fine. Great.
Thank you, Pradeep.
I'll be grateful for people.
Thank you.
Thank you, sir.
Shahin? Shahin is in mute.
Yeah, Shahin is in mute. Maybe
Shahin.
he must be talking to some people.
Oh, okay. So we wind up then, sir?
I hope so. There is nothing to say, then we can.
Shahin.
You can send a message on the chat, sir, or to reach out to Shahin, sir. Probably we can respond on that, I believe.
Okay, so anyway, we have finished the things, sir. Again,
Okay, sir. Okay, sir. Fine.
Thank you very much.
You can
And
close
all
the
the
session.
participants, I thank on behalf of the department. I thank everyone participated in this program. Thank you.
Okay. Thank you. Thank you.